Okay, so my talk will essentially go through this birth of quantum mechanics, Heisenberg's and matrix mechanics, Max Born, commutator bracket, Paul Dirac, quantization of the electromagnetic field. And I'll take a small digression and go to Pierre Fermat, Leonard Euler, and a bit of stories there. And then Schrodinger, how he got influenced by Hamilton's work, and then some quantum states of light and generation using nonlinear optical effects. Girolamo Cardano is an Italian mathematician, physician in the 16th century who came across two of the basic concepts of quantum mechanics, probability and complex numbers. He wanted to study mathematics, medicine. He didn't have enough money. So he started gambling. And he knew probability. So if you understand probability, you can gamble and keep winning. And he made a lot of money. And of course, he could study medicine. But unfortunately, at the end of his life, he lost all the money. That's the story. And he was also trying to solve cubic equations. At that time, there were a couple of Italians who were having competition of solution of cubic equations. Even negative numbers did not exist at that time. So he solved cubic equations and came across square root of negative numbers. And he called them mental tortures involved in working with them. He was not at all happy with that. So these two basic tenets, probability and imaginary complex numbers, are important in quantum mechanics. And of course, does quantum mechanics really require complex numbers? And I'll come back to this point at the end of my talk. There are experiments we conducted to check whether you can have really quantum mechanics based on real numbers. And this is information from Roger Penrose's very interesting book. So very quickly going through the birth of quantum mechanics, Planck tried to explain black body spectrum using the fact that oscillators can only absorb and emit in packets of energy S cross omega or h nu. Albert Einstein went on to explain photoelectric effect. And then he said light itself is quantized. See, Planck did not say light is quantized. The absorption and emission took place in quantum, but Einstein quantized the electromagnetic field itself. And then, of course, experiments by quantum scattering and so on. Then Rutherford did experiments on alpha scattering and found that atoms consist of a tiny positively charged nucleus surrounded by electrons. Now, the problem is electrons can't be stationary because you don't have a point where electrostatic fields can give you a stable point, Earnshaw theorem. So electrons have to be moving in the atom. And if they are moving around the nucleus, they are accelerating. And if they are accelerating, classical electromagnetic theory says that they have to radiate. And if they radiate, they will lose energy and fall into the nucleus. And so there comes Niels Bohr. He explained the spectrum of that is observed of atomic spectra by postulating that there are only certain quantized orbits which are allowed. And when the atom jumps from one state to another state, it emits light of a certain frequency. And so this interpretation was very good. These are all phenomenologically trying to explain, getting some results. And around the same time, 1925, 24, Louis de Broglie came with this matter wave theory, where he said matter also has wave properties, and he defined an equation relating wave aspects, wavelength, to the moment of the particle, which is p. And then Davison and Germer did experiments on electron diffraction and showed wave nature. And there comes Werner Heisenberg. Till that time, there was no consistent analysis, consistent theory explaining the behavior. And as you all know, 100 years ago, he went to Helgoland because he had some hay fever or something and was there trying to discover. And he said in classical mechanics, periodic motion is described in terms of a fundamental frequency. If there is an oscillation at frequency omega, you will see omega and harmonics of omega coming out. But that's not what is happening in atoms. Atoms are radiating not at frequencies and their harmonics, but in some different particular spectra. So he defined that we discard all hopes of observing hitherto unobservable quantities as position and period of the electron. I cannot observe the position, I cannot observe the period. But I will establish a theory which only gives relations between what is observable. So, for example, frequency of emission, the probability of emission, transition, which gives me the intensity of transition, and so on. So, people have been trying to analyze how did he come up with this idea at all. So, I will very briefly tell you that this is a Fourier series expansion of the position of the of an electron, and you have the Fourier expansion here, frequencies. So what he did was he replaced the Fourier frequencies by the transition frequencies between the state n and n minus alpha, and similarly the amplitudes here by a factor which is a n and n minus alpha. So now the frequencies and the probability transitions depend on two numbers n, one n and one n minus alpha, and there is the exponential factor which is the time dependence. So each element of this kind of a matrix, the matrix now, corresponds to a transition between two energy states. Now you find that if you define the frequency of emission in terms of energy, the frequency of emission from an atom from n to n minus beta is the sum of the frequency from n to n minus alpha and n minus alpha to n minus beta. So which means that the amplitudes must satisfy this equation because this is an exponential. In exponential, there is addition of frequencies. So in amplitude, there must be multiplication. And that's nothing but a matrix multiplication. In fact, he didn't realize that it was matrix multiplication. It was Born who later on found that out. And I think this is one of the most important steps in Heisenberg's paper, where he replaced Fourier coefficients by matrices. And he discovered that in quantum theory, observables are not in general commuting quantities. And a key reason is that quantum observables depend on two indices. And there came Max Born. And he says, one morning about July 10, 1925, I suddenly saw the light. Heisenberg's symbolic multiplication was nothing but matrix calculus. It seems around that time, matrices were not used by physicists much. It was primarily mathematicians who were using. Cayley had written down matrix theory. And then he wrote this equation. PQ minus QP is equal to H by 2 pi I. This commutational law is one of the most fundamental relations in quantum mechanics, 1925. And this equation contains discontinuity, non-commutativity, uncertainty, and complexity of the quantum world. It's an amazing equation which contains all this information in the simple, very simple equation. I is the unit matrix here. So Max Born says, an idea of Einstein's gave me the lead. He had tried to make the duality of particles, light quantum, or photons and waves, comprehensible by interpreting the square of the optical wave amplitude as probability density. Electric field square is proportional to probability density. This concept could at once be carried over to the psi function. Mod psi square ought to represent the probability density for electrons. That's Max Born's Nobel lecture. So he used Einstein's argument of relating photon amplitude to the probability to mod E square, and said that mod psi square must represent the probability density for electrons. And then comes Dirac. All this happening in the 1925, 1926, 1927 time scale. So Dirac believed that the non-commutative property of quantum mechanical quantities was of great importance. During one of his long Sunday walks, an idea came to him. There seemed to be a close similarity between a Poisson bracket and their commutator. Poisson bracket, which appears in classical mechanics. And then he said, the difference between the Heisenberg products of two quantum quantities is equal to IH bar times their Poisson bracket. And that he did the quantization. It's a very famous equation that you can find in Dirac's book. So Born and Jordan and Dirac independently discovered canonical quantization, thereby transformed Heisenberg's scheme into a complete theory closely related to classical Hamiltonian mechanics. So there came a fundamental theory which describes all the phenomena that were phenomenologically trying to be explained by various scientists. And then Dirac went on to quantize the electromagnetic field. A set of harmonic oscillators is equivalent to an assembly of bosons in stationary states with no interaction between them. If an oscillator of the set is in its nth quantum state, there are n bosons in the associated boson state. He could explain spontaneous emission. He introduced the entire bracket algebra in a paper in 1939. And a good notation can be of great value in helping the development of a theory. It's a very important aspect. Notations are extremely important because it can trigger you to discover something new. So I'll, with that, a brief discussion of quantization of electromagnetic field, and I'll come back to another story. Okay, so let me look at two experiments. One is a simple beam splitter. Single photons will light of very low intensity falling on this. Another is an interferometer. So the same setup in which I have recombined the two beams. Now, in this experiment, the photon always either appears here or here. There's no correlation between the outputs here. But here, if the system is completely symmetric, all photons appear in D2. How does the behavior of light depend on the experiment that we perform on it? Why should this photon behave like a particle? Why should the photon here behave like a wave? What happens if this is introduced after the photon has passed BS1? So at BS1, it decides to split or does not decide to split, for example. But once it has crossed BS1, I introduce beam splitter. So does it only appear here or where? So what happens if this is called the Dirac choice experiment, and people have done this experiment very well, and it still behaves the way it should behave if BS2 was there or not there. And quantum theory explains all these observations. So very briefly, you define a mode of an electromagnetic field as having a certain frequency, a certain polarization state, and a direction of propagation. So you can have horizontally polarized light with omega-1 frequency, horizontally with omega-2 frequency, or vertically with omega-1 frequency, and so on. Different propagation directions. They're all different modes, all modes of propagation. So you write down the electric field of the electromagnetic field, calculate the total energy of the electromagnetic field, and it comes out in this form. You just actually change variables, certain set of variables, and put it in this form. So this total energy happens to be the sum of energy of each mode. S represents a particular mode. And the energy of each mode resembles a harmonic oscillator. Half m omega square is squared by p squared by 2m. Similar equation here. And so we say that each electromagnetic mode behaves like a harmonic oscillator. And because we know how to quantize harmonic oscillators, we can immediately quantize electromagnetic field, and we get the total Hamiltonian in terms of sum of Hamiltonian of individual states. And the energy of each mode can only increase or decrease by s cross omega. And that particular quantum of excitation is called a photon. So it doesn't say whether it's a particle or a wave or anything. It's the quantum of excitation of that particular mode we call is as a photon, and the state is represented by ket n, where there are n photons in that state. And these are annihilation and creation operators, which are very familiar in harmonic oscillator, and they satisfy certain computation relations. A very general quantum state can be written as a linear combination of all the states, where this mod c square represents the probability of finding n1 photons in mode 1, n2 photons in mode 2, and so on. That's the most general state. We can look at couple of particular states. One is a vacuum state where there are no photons anywhere. N is 0 for all modes. You still find a electric field, a variance in the electric field, and that's a 0-point fluctuation. And if you plot the electric field, it varies with time. Average is 0, but average of the square is not 0. This particular 0-point fluctuation is responsible for spontaneous emission, the emission from this light, emission from the sun, and also responsible for the spontaneous parameter down conversion, which is a very important part of quantum optics, which I will very briefly cover. So actually, if you go back and look at these experiments, this particular single photon is being put in a superposition state of being both in the transmitted arm and in the reflected arm. So it is not that the photon is either reflected or transmitted. It is both in both arms in a superposition state. And in this state, if you do a measurement, you will either find it here or here, because it's a superposition state of the photon being here and here. And if you do the same analysis with this interferometer, you will find that the probability of detecting the photons in either of the arms depends on the phase shift introduced in the one of the arms of the interferometer. It's as if the photon is actually taking both paths. The probability amplitudes are crossing both of the arms, and you can actually even explain the Deloitte choice experiments. Some people call it changing the past, whether I can change what happens at this splitter by either introducing BS2 or not introducing BS2. So there are different quantum states. This is a single mode number state where you have a single one of the states occupied. You have a vacuum state. You have coherent states which satisfy certain equations. You have squeeze states which satisfy another set of equations. Entangled states, polarization, entangled states, and so on. So these are only very small sample. There was a talk of noon states in the morning. So all kinds of states are there, and I will just briefly touch upon some of them. So here are some plots of vacuum state, coherent state, squeeze amplitude squeeze state, phase squeeze states, squeeze vacuum state, and so on. So these are some of the states that come out automatically through a quantum mechanical analysis of the quantum states. So now I go to a small digression between, so it's a symbiosis between mechanics and optics, which actually was instrumental in inspiring Schrodinger with his wave equation. So let me start with Pierre Fermat. So he introduced this least time, the path of the least minimum time. It's in fact now it's stationary time, it's not minimum time. It could be maximum, it could be stationary. And so how does the light know at the start of the journey which path will result in minimum time? So Feynman modified that and got into the path integral formulation where he said light takes all paths. Certain paths interfere constructively and give you a classical path, which is the classical path that you observe, but all paths are being taken, are all possible. And he wrote this equation for the Fermat's principle. And at the time, actually, there was a lot of confusion between who was the discoverer of calculus. Leibniz claimed he's the discoverer. So there was a European team. There's Isaac Newton, of course, who claimed he is the inventor of classical mechanics. Calculus. So Bernoulli, Johann Bernoulli, posed a challenge. What is the curve that connects 2 points A and B, which will take minimum time for the child to slide? No friction. And what Bernoulli did was used optics to solve the problem. He had Fermat's principle, and Fermat's principle takes minimum time. So using Fermat's principle, he found out what is the path that will result in minimum time for the slide. And he obtained a cycloid. A cycloid, inverted cycloid. And it's actually really surprised Bernoulli. And it seems that the story goes, Newton got this challenge, solved the problem overnight, published in Philosophical Transactions without his name. And Bernoulli says, recognizing the lion by its claw mark. I recognize this must be only Newton. And in fact, at that time, only Johann Bernoulli, Newton, Jacob Bernoulli, his brother, Leibniz, and de l'Hopital had a solution to this. This was the beginning of calculus, the variations. It's a very interesting book, E.T. Bell, Men of Mathematics. So there is a chapter on nature versus nurture. You look at the Bernoulli family, Jacob Bernoulli, Bernoulli numbers, Johann Bernoulli, infinitesimal calculus, Nicolas Bernoulli, differential equation probability, Daniel Bernoulli, Bernoulli's principle. I mean, family consisting of outstanding mathematicians, 3 generations. So there's an interesting chapter on nature versus nurture in that book. Maybe interesting read. And there enters Leonhard Euler, a Swiss genius, a student of Johann Bernoulli. He says that Bernoulli was very busy and so refused flatly to give me private lessons. But he gave me much more valuable advice to start reading more difficult mathematical books on my own and to study them as diligently as I could. What a fantastic statement. He said that teacher didn't have time. So he asked me to read myself, and I read myself and understood everything. And there is a very interesting video by Professor Dunham on Euler and his genius. There was a check which is the most beautiful mathematical equations. And this equation 1, exponential IYQ plus 1 is equal to 0. It's an amazing equation. He has this E is a Euler number, and he is the inventor of this equation. Exponential Ix is cos x plus I sin x. And Lagrange was a very young man at that time, French-Italian mathematical physicist. And at the age of 19, he communicated Euler a general method of dealing with isoperimetrical problems. That's a calculus of variation problem. And Euler being himself, Euler did not publish. Euler courteously withheld for some time publication of some research of his own on the subject so that the young Lagrange might complete his investigations and claim the invention. What an amazing person that you allow somebody else to publish so that he can claim the invention, not you. And of course, it's still called Euler-Lagrange equation. And just to give you an idea, the lineage from Gottfried Leibniz to Johann Bernoulli to Leonhard Euler to Lagrange to Simon Poisson, this is all the guru and shishyas, line after line coming. And around the same time, we had Hamilton, who actually worked on optics first. We all know Hamilton in terms of mechanics, but all his investigations first were on the foundations of modern optics. And then he shifted into mechanics. And we all know this Hamilton's principle of least action, very similar to the Fermat's principle of least time. And you can actually define an optical Lagrangian, an optical Hamiltonian, and do the entire optics using what is called as Hamiltonian optics or Lagrangian optics. And the interesting thing is, knowing symmetries of the optical system, you can draw very general conclusions. Unlike simple ray equations and so on, you can, for example, things like what is the shape of a surface that renders parallel after reflection, all rays emanating from a point. We all know it's a parabola, but you can actually have problems which are very general and use these Hamiltonian principles to discover those solutions to those problems. So here comes Schrodinger. So in 19th century, Hamilton showed a connection between classical and mechanics and optics. So Schrodinger was familiar with this optical mechanical analogy, and in his paper he has written, the theory of propagation of light in a non-homogeneous medium, which Hamilton had developed about 10 years earlier, became, by its striking analogy, which occurred to him, the starting point for his famous theories in pure mechanics, Hamilton. So he connected the Hamiltonian mechanics and the optics into his mechanics system. So is one not greatly tempted to investigate whether the non-applicability of ordinary mechanics to micromechanical problems is perhaps of exactly the same kind as the non-applicability of geometrical optics to the phenomenon of diffraction or interference, and perhaps may be overcome in an exactly similar way. So he saw the analogy between geometrical optics and wave optics describing diffraction, geometrical optics deciding rays, and that allows him to introduce the wave equation. So we started from an equation like this, replaced energy, and you get the Schrodinger equation. And this equation is the famous equation. In fact, on its symmetry, there is this equation written here, I cross I dot equal xi. And he got all the solutions of the Schrodinger equation, which is now very well known, famous. And I'll just quote two things from his Nobel lecture, 1933. It seemed as if nature had realized one and the same law twice by entirely different means. In the case of light, with rays, and in the case of mass points, which was nothing but obvious. Attributing to the Hamilton's principle the operation of a wave mechanism on which the point mechanical processes are essentially based, just as one had long become accustomed to doing it in the case of phenomena relating to light and of the Fermat's principle. So he's actually, his ideas came from Hamilton's analysis or analogy between classical optics, ray optics or geometrical optics, and wave optics. So these coherent states, squeeze states, entangled states, they're all very important now. And so this coherent state, Schrodinger had worked way back in 1926. In fact, it was Lorentz who told Schrodinger that your type of solutions do not display classical motion. So Schrodinger realized that a Gaussian wave function could be constructed from a particular superposition of the discrete wave functions of a harmonic oscillator. And he introduced wave packets for the first time, and he introduced the superposition principle. Right? He superposed multiple solutions and got a wave packet, which is now the coherent state. And he says it's always possible to find solutions of the undulatory mechanics in the form of well-localized wave packets whose center of gravity oscillates without change of shape with the period of the corresponding classical motion. So he had already studied coherent states at that time. He had also studied entangled states much before the EPR paper came. Schrodinger's research notes show that Schrodinger's publication of 1935 in response to the EPR paper was a result of many years of reflection of the phenomenon of entanglement that he had been long aware of. Already in 1926, he struggled with that as a problem for a physical interpretation of wave mechanics. And also there are discussions in 1931 that he had a discussion with Einstein, and maybe Einstein got the idea of this EPR paper through his discussion with Schrodinger. And he, in fact, this is a very famous statement: entanglement is not one, but rather the characteristic trait of quantum mechanics. It's a very interesting article in an archive which you can read. Squeeze states were also invented way back in 1927 by Kennard, where he time evolution of a general Gaussian and a harmonic oscillator potential. He discovered all the squeeze states, showing that the variance oscillates between two numbers. And in a coherent state, the variance remains constant, while in a squeeze state, the variance keeps oscillating with time. So all this has been done way back in the 1920s. There are very interesting analogies between quantum states and light propagation states in parabolic index structures like optical fibers. You can see coherent states like a beam oscillating around the axis. Squeeze states, you have beams which are varying in bits like this. Phase squeeze states, vacuum squeeze state, and so on. So it's very interesting analogies which can become very interesting for students to understand the basics of what is exactly happening. So now I come to how to generate some of these quantum states of light. We all know use nonlinear optical interactions, one of the standard techniques now. So this is a linear term in polarization, electric polarization. There's a nonlinear term here, which is proportional to E square. And if you take three fields called the pump, signal, and idler, and calculate the nonlinear polarization, you will find new frequencies. And when you have polarization oscillating at different frequencies, it generates electromagnetic waves, because polarization is the source of electromagnetic waves. So you will generate second harmonic generation, some frequency, difference frequency, and so on. Now, so classically, you can actually solve Maxwell's equations and show that if you input a frequency omega, you can get a frequency 2 omega, second harmonic generation. But if you put 2 omega, you cannot generate omega, because incident omega can generate nonlinear polarization at 2 omega, but incident 2 omega cannot generate nonlinear polarization at omega. It can generate at 4 omega. So you don't get. But of course, experimentally, I do see the generation of photon pairs coming out of splitting of the input photon. So if you have a photon at frequency wavelength of 655 nanometers, it splits and generates photons at wavelength of say 1250 and 1370 nanometers. Of course, satisfying energy conservation. And this process is called spontaneous parametric down conversion. It's a spontaneous process. So what's happening is there's always vacuum fluctuation entering the crystal at all frequencies. Those frequencies which satisfy certain phase matching conditions will get amplified and generated in the process. And you see, depending on, this is a standard technique which is currently used called quasi-phase matching. You periodically reverse the nonlinear coefficient and satisfy momentum conservation for generation of photon pairs. And depending on the period you choose, you can modify the frequencies that are coming out, the polarization states, and so on. So it's a very interesting technique, now standard technique, which is used across the globe. So one of the interesting facts that happens is, if you put light at frequency 2 omega into a crystal, you generate two photons at frequency omega. A 2 omega frequency generates two photons at omega frequency, and you can show that this particular state is a squeeze state. That means it has a noise which is varying with time, variance which is varying with time, and goes below that of vacuum. Such squeeze states are important for applications in very sensitive sensors like interferometer, laser interferometer, gravitational wave observatory. And so you can see here that this particular simple technique generates squeeze vacuum state at frequency omega. And this particular, if in an interferometer, if you have just input and nothing here, you have a certain sensitivity. And if you put squeeze vacuum from here, you have a better sensitivity. Now, please remember, squeeze vacuum has photons. Vacuum has no photons. A squeeze vacuum has photons. And these are finite number of photons which are coming in, and you have better sensitivity. And as I said, LIGO is one very big application of this. Now, as I was mentioning, depending on the period that you choose, you can generate different pairs. For example, if I shine light which is horizontally polarized, I can generate a pair of light which are orthogonally polarized. I've marked them by different colors. One is called signal. Let me call the green as the signal and the red as the idler. Two different frequencies. So here the green is vertical, red is horizontal. Here the red is vertical and green is horizontal. This is just the opposite. So I have to choose a different period to satisfy a set of phase matching conditions, and I will get either this pair or this pair. Now, what happens if I engineer the crystal such that it has both these periods? Yeah, so it has, this is lambda 1 period I need, lambda 2 period I need. I make an engineered substrate which has both periods, lambda 1 and lambda 2. So now the photon, input photon, has a possibility of either splitting into green vertical and red horizontal, or red vertical and green horizontal. Now, if the two processes are indistinguishable, the output will be a superposition of the two output states, which is the polarization entangled state. Remember, in a double slit experiment, the photon can pass through the upper slit or the lower slit. If you have no information on which slit the photon has taken, which path the photon has taken, you will find interference. If you have information, you don't have to have information in your head. There is information somewhere in the experiment which can allow you to find out which slit the photon has passed through. There is no interference. Exactly similarly, if the two paths are indistinguishable, they interfere and produce a amplitude sum of this particular quantum state and this particular quantum state, and that's a polarization entangled state. So it just comes about because of the existence of indistinguishable paths, two of them, which interfere. Now, classically, one can think that, okay, so I have either this pair or this pair coming up. So if I split the two photons into two arms, so there are beam splitters which are dichroic beam splitters. So red reflects, green passes through. So I put vertically polarized, horizontally polarized, or horizontally polarized, vertically polarized. I will get bit sequence which are perfectly correlated. There's no quantum mechanics involved. It's a classical explanation because the photons are either this way or this way. So if it is this way, and if the pass axis is vertical and horizontal, they will both pass through. If it is this one and if it is other orientation, none of them will pass through. So there's no problem. The problem arises if you change the orientation of the analyzer. If you make it at 45 plus 45 minus 45, this has a 50% chance of going, this has a 50% chance of going, and classically there is no connection. Sometimes this may go through, this may not go through, sometimes this may not go through, this may go through. It's like coin toss. I mean, both of them can go through, both of them will not go through. You do the experiment, perfect correlation. And that is where entanglement comes in, because this particular state is a state of polarization entanglement where projecting one of the photons into a known state, into a state, immediately projects the other entangled photon into an orthogonal state. There is no classical explanation for this. This is a purely quantum mechanical effect, quantum mechanical explanation it needs. So this is a typical polarization entangled state, one of the entangled states. It cannot be written as a product of signal or idle states. You can check that this is exactly 2 photons, and the polarization state of either the signal or idler is undefined. That means you pass the signal through an analyzer and rotate, you'll always get 50% chance of passing through. And measuring the polarization state of one of them immediately projects the other into an orthogonal state, no matter what. It could be circular polarization, left circular, right circular, left elliptical, right elliptical, horizontal, vertical, nothing. Any 2 orthogonal polarization bases you take, this will become, this is an entangled state. And this is what Einstein was very much against, calling this spooking action at a distance. So you can have entanglement in multiple different degrees of freedom. It can be polarization, it can be spatial mode, frequencies, there can be hyperentanglement. I'll just give you a couple of examples which we had been working on. All our work has been based on waveguides. So you can generate entanglement between modes of different modes of the waveguide. For example, it could be an entanglement between the fundamental mode of signal and excited mode of idler, and that's the mode entangled state. It could have application in quantum computing. You can have higher dimensional entangled state where you have 2 photons but appearing in multiple states. So you can have here, for example, both photons exit from here, or both of them exit from here, or both of them exit from here. So I can have multiple combinations with 2 photons in multi-dimensional space. So higher dimensional entanglement states. I could also have hybrid entanglement, where I have an entanglement between the polarization state of one photon and the mode of the other photon. So the signal is in the fundamental mode here and first excited mode here. Idler is always in the fundamental mode, but in vertical state and horizontal state. So depending on what polarization you pass on the idler, the spatial mode of the signal will change itself. It's a very interesting entanglement state where you have entanglement between 2 different degrees of freedom of the 2 photons. And there are multiple applications of entanglement in computing, encrypting, teleporting information, and so on. And one of them is quantum key distribution, which a lot of people in India are also working on, where you can use entangled photons. Because of complete correlation between Alice and Bob detectors, any eavesdropper can be immediately picked up by the detectors and solved. Okay, so I have been seeing some recent papers on real valued versus complex valued quantum mechanics. So there are some experiments which have been conducted where you generate 2 pairs of entangled states. So you have correlation between A, B, and C, 3-party correlations, and the measurement of 3-party correlation. Real quantum mechanics predicts a limit of 7.66. Complex quantum mechanics 8.49. Experiment is showing 8.09. The question is, of course, there are still some believers who think complexness numbers are not necessary in quantum mechanics. Why should we have a complex number? So there are people who are trying to do experiments to check whether real quantum mechanics can explain. I think there are still experiments that are going on to validate some of these interesting aspects of entanglement and quantum mechanics itself. So there are people who work on bulk devices, bulk crystals, bulk optics. Of course, if you want to have a real commercial application of quantum computing and quantum information, you need to have everything in a chip. And that's where integrated quantum photonics comes in, where you have waveguides, optical waveguides, which transmit light, and you have all operations on the waveguides. You can have switching, you can have modulation, you can have a spontaneous parameter Dunn conversion, and so on. So there are certain advantages of generating light in waveguide, and compact quantum photonic devices, much like electronic integrated circuits. So there are a lot of people working on this, and I'm sure with time, with more and more development. For example, way back in 2018, there is a interferometer here which has been built with 550 optical components, with a lot of Max-Zehnder interferometers, directional coupler switches, electronics, etc. And here is a recent one on integrated quantum photonic space sensor using squeezed light. So you have one which has a beam splitter with a second harmonic generator, optical amplifier, signal interferometer, and everything, and all in a single chip. So the application of integrated circuits, optical integrated circuits, and quantum photonics is becoming more and more important. And these 3 people were awarded the Nobel Prize in 2022: Alan Aspect, John Clauser and Anton Zeilinger. So as I mentioned, there is a book which is coming out maybe later this month or next month, published by Stringer on integrated quantum photonics, where I've tried to give you some gist of integrated optics, nonlinear optics, and quantum optics, quantum photonics into that. So that's the summary. 1925, Werner Heisenberg proposed matrix mechanics. 26, Schrodinger works out wave equation. 27, Dirac quantizes the electromagnetic field, bracket algebra. Then there's a lot of generating, analyzing non-classical states of light. Next decade is expected with further developments from both basic science point of view. And of course, the more interesting problems are what is actually the nature of reality. And I think some of this quantum mechanical understanding will actually lead us to better understanding of perhaps consciousness, reality, observed, relationship between the observed observer and the observation. So there is a meme which I saw, Max Planck, inspiration, exploration, and desperation. So I thought I'll just post it as a final slide for you to go back with. Thank you. Thank you very much for your patient listening.
Yeah, so thank Professor Tyagarajan for this wonderful talk, and the forum is open for questions. I'm sure there should be questions from the students.
I think that was in the gravitational wave phenomenon. Because that was a state which existed, new from 1927 onwards, but I think when it came to interferometers and sensor, and people realized that it can help us to go much better sensitivity than normal states, coordinate states, for example.
Yeah, apart from mathematics, is there a way to think about how squeeze states give us photon emission from excited states?
How squeeze states, sorry?
Not squeeze states, sorry. The vacuum fluctuations give us photon from excited states. Apart from mathematics we can sort of see it, but is there any other way to think about it?
I think the point is that there is never a pitch dark state, which means no electric field, no magnetic field. It's like I cannot put a harmonic oscillator in complete rest. So in a similar fashion, I cannot have a situation where there are no electric and magnetic fields at all. So if there are electric and magnetic fields and electromagnetic fields at all frequencies, they can induce down conversion from 2 omega to omega. So this similarly, see, in quantum mechanics, we are taught that energy levels of atoms are stationary states, E1, E2. So once I put an atom in E2, why should it come down? It is a stationary state. We say we go to lower energy. Why should I go to lower energy? What defines that I should go to a lower energy? No, there's no definition. No. I can be in a higher energy state. So it is the vacuum fluctuation which is not allowing it to sit there. It's constantly interacting at all frequencies. So it pushes it down. So similarly here, if I put a frequency omega p into the crystal, I am not putting anything else, but it's there at all frequencies. And those frequencies that satisfy the momentum conservation condition will get generated in the process. And that has no classical explanation again. Yeah.
Thank you very much for the wonderful talk. So it looks like a lot of the developments, basic developments done on quantum mechanics in the 20th century. Some I didn't know about these coherent states and squeeze states already investigated in the 20s. It looks like there is not much new to be done in the 21st century. So could you single out from the developments in the 21st century, what is, in your opinion, that are fundamental, or what could it be? I mean, what?
No, but Glauber got the Nobel Prize for coherent states.
You mentioned consciousness and relation with maybe the measurement problem, etc. No, those seem to be very tough, right?
Yeah, so I think although the states were analyzed in 1926-27, their practical implication was understood much later. And I think the fact that Glauber got the Nobel Prize for his work on coherent states, so all that work which he did and understanding laser light, noise, and of course squeeze states for their applications. And entangled states he had worked, but of course EPR paper was the main paper that came up and pushed Schrodinger further. But it seems there are a couple of papers which I put reference here, which discuss this aspect, that from his notes, pull out his notes and trying to find out what was Schrodinger's thought at that time itself when he had written the equation, and what was his things that he was looking at. And it seems he had discussions with Einstein on some of these basic issues of interpretation itself. So I think with the development of technology, being able to control single atoms, single photons, and so on, I think the importance is becoming much, much more clear. And it will become more and more important in our information communication technologies. Whether it is good for the human society or not, that I don't know.
Thank you for a wonderful talk. I'm an experimentalist. I remember when Carl Cave said, if you have enough photons to get better signal to noise, don't do quantum, right? And I mean, you have now people that claim that there is entanglement and quantumness in sources that have many, many photons, 10,000, 100,000 photons. As far as I understand it, most of the metrology to understand whether something is quantum or entangled acts on the fact that you cannot divide a photon, and then you play on this in different protocols, and they might be more mysterious or not, but that's how we characterize it. Do you see any way to now scale this to sources with many more photons?
I think that's a problem which people are facing for quite some time. So there were this Greenberg-Zeilinger states, GHZ states. But I think the problem is beyond 2 photons. There are experiments, but the production rates become in hertz rather than in megahertz. So you then have to live with a lot of time to integrate. But I think there are also people who work on making multiple SPDC sources and delaying the photons, detecting one of the pairs and then detecting the other one, and making a source which has multiple number of photons coming one behind the other, a regular pattern or whatever it is. So I think, I don't know, maybe whether this nonlinear optical technique will lead to, say, 20 photons entangled, I'm not sure. I'm not so sure. There are deeper issues involved in that. Because the moment I try to increase the power level, so there are people who worked on chi-3 nonlinearity, which is third order, which can, like second harmonic, inverse of second harmonic, I can have an inverse of third harmonic. So 3 omega photons splitting into omega, 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 3 photons. But again, those efficiencies are very low. Those efficiencies are very low in terms of production, in terms of analysis.
So I'm talking about high order harmonic generation, which seems a bit ludicrous, right? You use high, strong fields in order to get quantumness. Typically, we associate quantumness, at least I did, with feeble light fields and so on. And there's some indications that there is some kind of maybe entanglement. I want to be careful with the language between the different emitted harmonic modes, 3, 5, or 5, 7, and so on. And the problem is how to characterize this, right? Because one trick, of course, is a dirty trick to say, I have 10,000 photons, I attenuate by a nonlinear process, and I do single photon counting. But then you assume that nothing is lost in that process. That's why I was asking, right?
Yeah, sorry, I wouldn't be able to answer that question. I don't. I would myself have to look around and see what happens to these sources which claim to have 10,000 photons which are
right
entangled or whatever it is. Yeah.
Maybe next book. Thank you.
So my question is from a perspective of a student, actually. So since you drew this nice connection between classical mechanics and quantum mechanics, So let's say, can I straightforward way, I can extend Emmy-Noether's theorem to quantum domain? To every symmetry, there is a corresponding conserved quantity.
Perhaps I have not looked at it. Perhaps.
I see.
In fact, I can quantize ray equation and get wave equation.
Yes.
Using similar principles like you do quantizing classical mechanics to quantum mechanics, I can start from the ray picture and go into quantized light rays, which become a wave equation.
My question was because does it violate any of the uncertainty principle, those things, if you talk about these conserved quantities from that angle? Do you know of any issue or something?
No, I have
regarding
not
that?
looked at it.
Okay,
No,
okay, thanks.
Yeah.
So
Here. Somebody, yeah, sorry.
this is just a confirmation. So you were mentioning about the vacuum fluctuations, right? So that is, it's pure random, like, and it is independent of everything.
Yeah.
Whatever, irrespective of the environment, it's still just no way of controlling it at all. Nothing.
No.
Thank you.
So even if you have what you call as a monochromatic wave, classical monochromatic wave, it is noisy. There is noise on sitting on that classical electromagnetic wave, which is supposed to be E naught cos omega t. It's never E naught plus delta E is there all the time. That vacuum fluctuation is always riding on top of the wave itself.
No, I found that experiment absolutely remarkable, where you have the analyzers at plus 45 and minus 45, and despite that, I suppose that's experimentally realized, right? That they're perfectly correlated. So, and whether they're horizontal and vertical, or they're at plus 45 and they're perfectly correlated, that means probably for every angle they will be perfectly correlated. So, in fact, if you don't even have the analyzer size, yeah, they should be still correlated, right? So
they are correlated, but unless you make a measurement, you can continue doing experiments with those until you make a measurement. At that time, you will see all the effects of this correlation. Till then, you don't see them.
Yeah. I didn't know of this, and I find that absolutely remarkable.
So the fact that whatever you do on one photon is actually affecting the other photon, that is the problem. So that's what's actually happening. If you project and do a measurement on that, on one of the photons, the other one instantaneous seems to occupy an orthogonal state, irrespective of whether it is a linear polarization or circular polarization or elliptical polarization, whatever it is. It doesn't matter as long as there are two orthogonal states.
I think, okay, the last.
Joy, yeah.
Yes, I just wanted a small clarification about that hybrid entangled state that you talked about. Polarization and so the state looked different. I was wondering if
so it is between the signal is horizontally polarized between mode 0 and mode 1. Here, the photo shows, the picture shows.
And the
idler is always in the fundamental mode, but it is vertical and horizontal polarized. So if you happen to pass the idler through a vertical polarizer, the signal occupies the fundamental mode. If you pass the idler through a horizontal polarizer, you will see the signal in the first excited mode. If you pass it at 45 degrees, then the signal becomes a linear combination of the fundamental and first excited mode. So there is a very interesting video from Zeilinger's group where they have not done this method, but using a spatial light modulator, they have make hybrid entanglement. And as you rotate the polarizer on one of the photons, the spatial mode state of the other photon continuously changes. Real-time entanglement variation with time, actually. So they have shown that it's an instantaneous effect. So depending on the polarizer analyzer you use for the idler, the spatial mode of the signal changes as a linear combination. Because then I will write that state in terms of, say, 45 plus 45. And so it gets modified to HS0 plus HS1, the states which are fundamental and first sector.
Right. The signal polarization is always horizontal.
Yeah. Here, in this example, it's horizontal. Yeah.
Okay, the absolutely last.
One question, so I'll ask a half a question. So
you have full answer.
Are there any, you can decide.
So are there any other degrees of freedom that can be used? So you have said mode and polarization as two degrees of freedom.
Time of emission, energy.
For
Frequency.
entanglement purpose.
Time of emission, frequency.
Orbital angular momentum comes
Yes,
in mode,
yes.
mode itself, right? I mean, it is part of the mode family.
Orbital.
Okay, time and then wavelength.
Frequency.
Yeah, frequency.
Frequency, yeah. Frequency entangled state.
So okay, so all of them, you will say that they should obey the same entanglement criteria that one needs to kind of show that it is entangled in the quantum state, kind of a thing. Should we assume that?
Yes. So they have to satisfy certain criteria, which is independent of the degree of freedom. If it's a spatial mode entangled, it's a particular. So you have to. So what happens when you project one of the photons in a particular spatial mode? What happens to the other photon? Like in your optical angular momentum mode, if they are entangled, then depending on the measurement you do of the photon of one of the photons, the momentum of the angular momentum of the other photon, we will jump into another particular entangled state. They are another corresponding state. Yeah. Thanks.
So with that, let us thank Professor Tyagarajan again.
Thank you for a patient listening at the end of the day.